Probability distribution, mean, and histogram for data collected from a sample. In our previous example, we conducted a theoretical probability experiment of flipping coins 3 times and then previously 2 times. In this example, we're going to look at data collected from an actual sample. A child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following was obtained. Let X equal the number of times per week a newborn baby's crying wakes its mother after midnight. And for this example, X is going to be the values from 0 through 5. 0, 1, 2, 3, 4, and 5. So we have the following data. 2 babies out of the 50 didn't wake their mothers after midnight. So that's a value of X equals 0 because they didn't wake their mothers at all. 11 babies woke their mothers once after midnight. So that's a value of X equal 1 because X represents the number of times the baby wakes its mother, and therefore if these babies woke their mother once, this value of X is 1. Then 23 babies woke their mothers twice after midnight. This is a value of X equal 2 for 2 times. 9 babies woke their mothers 3 times after midnight, and that's X equal 3. 4 babies woke their mothers 4 times after midnight. That's a value of X equal 4. 5 babies woke their mothers 5 times after midnight. That's a value of X equal 5. So for this example, we are not going to be building a tree diagram and answering our probability questions based on a list of outcomes from a tree diagram. Because this is taken from a sample, we are going to use these sample numbers to calculate our probabilities. So here are the numbers again. I'm going to keep them up here while we work on this next part. Our probability distribution table starts with 2 columns, the value of X and then the values for P of X. Now the values of X are these numbers. They go from X equals 0 to X equals 5, and sometimes these values of X are not given to you, and you have to be able to discern that value of X by reading the problem. So 2 babies didn't wake their mother after midnight. That means that they didn't wake their mothers at all, so value of X is 0 for none. Woke their mother once, that would be a 1, and twice would be a 2. So sometimes you're responsible for coming up with these values of X on your own. So we label those values of X in the first column. Now, for the values of P of X, there's no tree diagram to refer to. So what we're going to do for this is actually easier sometimes. Some students believe it's easier than a tree diagram. It's just a matter of taking the number over here, the 2 babies, dividing it by the total number of values in the sample, that's 50. 2 divided by 50, and getting our probability that way. So our probability for the first row would be 0.04. 2 divided by 50 is 0.04, and that's 4%. And we're going to do that for the remaining values of X as well, using the number here in the numerator of the fraction and the value 50 in the denominator, because there are 50 babies total in this sample. So we're going to take 11 divided by 50 for the next one and get 0.22 or 22%. Take 23 divided by 50 when X equals 2. That's 0.46 or 46%. 9 divided by 50 when X equals 3. That's 0.18 or 18%. 4 divided by 50 when X equals 4. That's 0.08 or 8%. And 1 divided by 50 when X equals 5, that's 0.02 or 2%. So if we want to verify our work like we've done in the past, we can sum up the values of the values of P of X in this column, add all these decimals up, and you will get 1.0, or add all these percentages up, and you will get 100.0. So from there, add a third column to the probability distribution table. And that third column is going to be x times p of x. So here are your first two columns that we created. And x times p of x, remember, we're going to take this value, 0, multiplied by 0.04, put the answer here, and that would be 0. Take 1, multiplied by 0.22, put the answer here, that's 0.22. And you continue throughout the rest of the table. 2 times 0.46 is 0.92, 3 times 0.18 is 0.54, 4 times 0.08 is 0.32, and 5 times 0.02 is 0.10. When you add these numbers up in the third column, you have the average expected value, or the mean, for the long-run behavior of this experiment. So it's denoted by the symbol mu, and when we add all those numbers up, you get a value of 2.1. Now, to interpret what that 2.1 means, consider what the experiment is. The experiment involved babies waking their mothers at night, newborn babies waking their mothers at night. So here's the interpretation. You would expect on average a newborn baby to wake its mother after midnight 2.1 times per week. That's how you would interpret this 2.1 meaning. Go back to the original experiment, which was the number of times the baby woke its mother per week, and that's how you interpret the average. If you were to take this experiment and conduct it over many babies over time. Okay, the next part of this experiment involves building a histogram from our probability distribution table. So we are going to have our horizontal axis with the values of x and our vertical axis with the values of p of x. So here's our horizontal axis. X represents the number of times a newborn wakes its mother in a week. 0, 1, 2, 3, 4, 5. Our values go from x equals 0 to x equals 5. And p of x is on the vertical. And I labeled p of x in increments of 0.05. So 0.05, 0.10, 0.15, 0.20, and so forth. And then you build your histogram by creating rectangles that are the same height as the probability for that value of x. So our first value of x was, let's go back and remember, first value of p of x was 0.04, then 0.22, then 0.46. So it's approximately 0.04, then approximately 0.02, and then approximately 0.46. So it does appear that this graph here was computer generated, and it was, but it's not my intention to have you do this on your computer or your calculator. I expect this to be done just on paper. So you sketch your axes first, and then you sketch rectangles as neat as you possibly can on a piece of paper. So you would not do it on your calculator. Okay, we're going to next answer some probability questions based on this experiment. So what's the probability that a newborn wakes its mother after midnight twice this week? So let's go back and look at our distribution table. That's the easiest way for us to answer the question. So the probability that a newborn wakes its mother twice this week is to take a value of x equal to 2 and then look at the probability associated with that value of x. So the answer to this question would be 0.46 or 46%, because that's the probability of a newborn waking its mother twice this week. So let's go and answer the next one. What's the probability that a newborn wakes its mother after midnight more than 3 times this week? So more than 3. Okay. More than 3 refers to the values of x of 4 and 5. So if we want to find the probability of a newborn waking its mother 4 or 5 times this week, we would sum up the value of x equal 4 the p of x equal 4 and the p of x equal 5. So in this case, that would be a value of 0.08 plus 0.02 or 0.10. The probability of a newborn waking its mother more than 3 times this week is 0.10 or 10%. Okay. What's the probability that a newborn wakes its mother after midnight at most 2 times this week? So at most 2 refers to the values of x of 0, 1, or 2. So 0, 1, or 2, we will add up those values and we'll get 0.72, and I'll demo how to do that here. 0, 1, 2, so 0.04 plus 0.22 plus 0.46 is 0.72. So you're adding up these three probabilities at most 2, these three right here. And that would conclude this complete problem. So that's how you do a probability experiment when it involves sample data. And we have one more example like this now.